This video wraps up a series of presentations covering key concepts of multithreading and synchronization. This presentation provides a summary of the various approaches and methods that were covered in this series for multithreading. Recollect, in this series, we covered different kinds of multithreading approaches. First, we focused on synchronization-free approaches. That means these approaches do not use any mutex, and these are the preferred and fastest approaches for multithreading. We looked at data parallel applications, and then under data parallel, we also looked at reduction as an approach for implementing data parallel applications. Then we also looked at task parallel applications where each thread was performing different algorithms or operations but with the same data, while the data parallel approach, on the other hand, worked or applied the same algorithm to different data sets. Then we covered synchronization-based approaches where there is at least one mutex involved in each one of these problems. Typically, there are more than one mutex involved in most of the synchronization-based approaches. First, we looked at using a mutex with a lock guard for creating and establishing critical sections. Then we looked at using multiple separate mutexes to increase concurrency and improve parallelism in our multi-threaded programs. Then we looked at using multiple mutexes simultaneously, where two or more mutexes had to be locked at the same time in order to implement certain types of problems. And this is where we use the dining philosopher model to help us remember to lock multiple resources simultaneously. Then we looked at a more sophisticated approach for managing threads doing different operations using the producer-consumer approach. Here we looked at two different strategies for implementing the producer-consumer model. The first one was using busy wait or spin locks, versus the second one was a little bit more sophisticated using sleep-wakeup approach based on condition variables. Let's do a quick summary and a thought flow on how to implement or utilize these different approaches for multithreading. First part of the work is to identify the program or parts of the program that need to be multithreaded in order to improve performance. And this is the first step that you will typically start with, is measuring and timing the program. We looked at the use of USR bin time, which is a standard software tool in the GNU Linux distribution. And you can use USR bin time to monitor and measure and record different runtime properties of the program. Specifically, we looked at user time, that is the total time for running the program, system time, that is time spent in making syscalls, the elapsed time, which is the time that a user would observe if the program was run, and of course the percentage CPU that tells us how effectively the different threads are running and utilizing the CPU resources. And this timing is important so that as you multi-thread your program, you should see a steady improvement or use these timing measurements as benchmarks to say if your implementation for multi-threading is effective and efficient. So first, you should always try to invest best effort to accomplish multithreading without requiring any synchronization. Remember, synchronization essentially reduces a multi-threaded program to a single-threaded program in the critical sections. So the more critical sections you have, the slower your program will eventually be, no matter how many resources you throw at it. So the first rule of work is to try to accomplish the multi-threaded solution as a data parallel or synchronization-free method. So if you look at multi-threading without synchronization, this is where threads operate independently on their own memory locations, and threads do not step on each other's stores or use other memory locations. Particularly, this applies only to the information they're updating. Read-only variables is not an issue. It's only where you have to update values where the problem comes. And here threads operate on their own memory locations, and this is the kind of synchronization-free methods or programs and problems that we have looked at initially. Under this category, the first thing you have to think about is how much data you're handling at any given time. So typically, if you have only a small amount of data or you have one-time requests that come in, so you're developing like a multi-threaded web server or something like that, then you should try and use stood async for doing some of these operations because async is much easier for you to implement. Remember, we looked at async where it's a method that calls another method on a separate thread. So stood async is a standard method you call, and you give it the method it should call. It calls the method from a separate thread and gives you the result back. Recollect that you can, with the asyncs, you get what are known as future objects. That means you get the result after the thread is finished. So that means async gives you a future object from where you can get the result. And you would use a standard two loop operation. If you want to use multiple asyncs, you will use a two loop pattern where the first loop starts off all of the threads by calling multiple asyncs and stores the future from each one of those calls, and then uses the get method on the future to obtain the results once the thread has completed operations. So using these stood async can make your life easier, but you would typically use it only for small data or one-time operations in a program. The other alternative is where you have big data or many repeated operations you want to perform and you want to get the results from these operations. Then you should try and partition the problem or the data into n threads. So here we've typically looked at problems where we evenly partition the data between multiple threads, or your partitioning can vary depending on how much workload you anticipate for each thread to have. And this kind of a data parallel application is widely used in image processing, video conversions, and a lot of the other operations that work with bigger pieces of data or big data analysis would use this type of an approach. And keep in mind here, each thread operates or works on a subset of the data doing some processing. And they all operate on independent memory locations. That means no two thread operate on the same piece of data. Therefore, there is no synchronization required. Again, we have the same two loop pattern here. The first loop will always spin up all of the threads, and the second loop will wait for all of the threads to finish. We looked at another approach called reduction. This is where we want to take many data items and reduce it to one result or a few results. So here, for example, if you were to find sum of numbers, you would partition them between different threads. Each thread will figure out its local result, and then finally, it'll reduce millions of numbers down to a few numbers. Then the main thread can operate on those few numbers and calculate the final result. And this operation is called reduction. Again, here we do not use any synchronization because all of the threads are operating on independent subsetted data items. And these subset of approaches are the approaches that we use without synchronization, and this should be a first strategy for multithreading is to try and multithread without synchronization. However, many problems will require some kind of synchronization to be accomplished. So first, before you get into the synchronization, ensure that you can ensure you try and do it without synchronization. And then when you do the synchronization, keep the 4 rules for establishing an effective critical section in mind. First, no two threads should ever be in the same critical section simultaneously. So you should try and use the appropriate mutex logically associated with each resource, and you should consistently lock it in every place. It could be accessed in different methods, so you have to make sure you consistently lock it throughout your program. You should not make any assumptions about speed or number of cores or CPUs. So that means when you write your multi-threaded program, you should always have a mental model of how different things can happen at different times, and you should be able to keep that mental model of different things happening and try to see if you're able to cover all of the different scenarios that could arise during multi-threading. And this having this mental model does take a lot of practice and training. So building strength on the mental model only comes through practice. So you have to constantly work on it. No thread outside the critical section may block a thread in the critical section is also important. So that means you use your mutexes appropriately to ensure this kind of a situation does not arise. And no thread should have to wait too long to enter its critical section. This basically means that you have to keep your critical sections really, really short. Usually milliseconds is about what is recommended for critical sections on modern computing devices. So you have to try to keep your critical sections really fast. All right. In the synchronization-based approaches, first thing you have to think about is how many resources do you have to lock at any given time. So the first and the simple one is to see if threads can get away with just locking one resource at a time. That means you have a problem where only one resource, one shared resource needs to be locked. And then most of the threads are doing similar operations. That means the time that they're going to spend doing some operation and the time spent in the critical section, etc., is all about the same. First, try to see if you can use atomic variables where possible. So this is where you would use stood atomic to create those shared variables. Keep in mind with atomics, when you do operations on them, by default, the hardware, these are implemented in the hardware by the CPU, and they are reasonably fast, and they are guaranteed to be thread safe. That means there will not be a race condition when you do operations on atomic variables. So try and use atomics because they are relatively straightforward. However, keep in mind, you can only use primitive data types with atomics because these are supported by the CPU, and the hardware can only do those primitive data types. It will not handle objects like strings, unordered maps, vectors, etc. So if you can work with primitive data types, then try and work with atomic first. If that doesn't work, that means you cannot use atomics, then you would have to go using one mutex per shared resource and ensure you keep the critical sections as short as possible here. So for each resource, you would have a separate mutex or a separate lock. This is to ensure that you maximize concurrency and maximize the opportunities for threads to operate independently. So each thread can lock a separate mutex. We looked at examples where we can create a list of mutexes, one mutex per resource, and each thread appropriately locks the corresponding mutex to do the different operations on those threads. So try and use as many mutexes as you can based on the number of shared resources so you maximize concurrency. That means how many simultaneous threads can operate. You increase the concurrency in your model. All right, now let's look at another scenario where threads are doing very different types of operations. That means the time that it takes to do the different operations is substantially different. Then in this case, we looked at the producer-consumer model. This is one of the more sophisticated or complex models that we looked at, where some threads are organized as producers, some threads are organized as consumers, and they operate with a shared queue. And this is a common pattern that is used in a lot of online transaction processing systems where there are shared queues and different numbers of threads operate on different subsets of the systems to try and maximize the overall system throughput and performance by utilizing resources effectively. So here the number of threads is a balance. You can have a few fast producers and many slow consumers, or many slow producers and a few fast consumers. This is such that the resources are effectively used by balancing the work that is being done on the CPU. Here we looked at examples where we use a shared queue. We looked at simple examples with one producer, one consumer, so we have a good mental model on it. And initially, we started looking at using a busy wait approach for processing. Then we looked at a sleep-wake-up approach where we used a condition variable and a unique lock to lock and unlock these resources and wait for certain conditions to be met before we proceed into the critical section and do operations. So here we also looked at how to use the condition variables with the wait method. So we say wait until certain condition is met. And here the conditions were represented as short anonymous methods called lambdas. And these lambdas gave us a convenient, quick way to represent some logic associated with the waiting condition. Instead of lambdas, we can use other methods too, but here using lambdas makes the code a little bit short and easy to read and somewhat easier to understand. So that's the idea of using those lambdas in the context of this sleep wake up and the condition variables. Of course, we also looked at the timing comparisons between spin locks versus the sleep-wake-up model. With the busy wait or the spin lock, the threads constantly are working, they're running, checking for work to be ready, so they utilize a lot more CPU resource, but the threads respond very quickly. So this busy wait or spin lock approach is great for online or very interactive problems where you're developing games or you want to develop self-driving cars and such where you need quick response times. Then the busy wait or the spin lock approach is a good way to go. Here you're trading off quick response time by but increase energy usage. The sleep wake up, on the other hand side, is more energy efficient because threads do not utilize CPU when they are idle. So it gives you more energy efficiency, but it does have a little bit overhead to wake up these threads and send and receive these notifications. So the response time for these threads will be a little bit higher, so it's a trade-off between energy versus response time. So you kind of have to think about what type of problem you're working with, which one is the more important criteria that you want to meet. And then based on that, you would choose the appropriate strategy to implement the producer-consumer model. Notice that all of these approaches here work with a single mutex. That means a thread needs only one resource to be locked at any given time. However, if a thread requires multiple resources to be locked, this is even more complicated of a scenario. And then this is where we use the dining philosopher's model to give us a mental picture to understand that we need to lock two resources simultaneously. This is where we looked at the dining philosopher's model, where a philosopher needs to lock or pick up two chopsticks simultaneously to eat. That means do some operation in the critical section. So the key idea of locking multiple resources is important because we looked at cases where locking one resource at a time could potentially lead the system to a deadlock. In simple cases, it is easy to identify these deadlocks, but as the program becomes more and more complicated, it gets much harder to identify these deadlock situations. So it is important to keep in mind that we have to lock these mutexes simultaneously. So this is where we looked at the stood lock method, where we specify all of the mutexes that need to be locked in one shot. And the stood lock method internally uses deadlock avoidance algorithms. That means it actually looks at how the mutexes are being locked and used and uses algorithms to ensure that you will not get into a deadlock, but lock both the mutexes simultaneously so you can establish critical sections where you're utilizing two or more resources simultaneously. It is also important to ensure that you unlock these mutexes at the end of it. So these are all of the different methods that we looked at, and it's important to keep this whole thought process flowchart in mind as to how you go about trying to decide which one of these methods to apply depending on what type of a problem you're trying to solve. So keep this flowchart in mind in trying to help you identify and decide which model to use for which problem. Keep in mind, multi-threading is a pretty complex topic, and you will keep on working on it in your jobs and careers, and it takes a while to kind of get your hang of multi-threading and wrap your head around it. In this series, we have only covered some of the basics. And that means we're just starting the journey in this series, and then it's up to you to continue this journey through this multi-threading topic for the rest of your careers. There are several different classes, additional mutex classes and threading classes that are available that you can check out. There are many different mechanisms. There are so many reader-writer locks and other types of locks. You can have shared locks and you can move the locks around between different threads. There are lots of different patterns for multi-threading that you can explore. And all of these are available on the standard online standard documentation for C++. And there are some pretty decent examples that you can look at and try to follow along as you continue your journey into multi-threading. Thank you for watching this presentation. Hope you found it useful. Don't forget to check out all of the presentations in the series to get a better understanding of multi-threading and modern C++ libraries that help us with multi-threading.